Hello everyone. We will now begin our lecture on chapter 2.5, which is on zeros of polynomial functions. Now what we mean by zeros is finding the points where the y values are going to be 0. So we know that all along the x-axis, any point, all right, any point on the x-axis will have a y value equal to 0. So in this section, we are interested in finding at what value of x will the graph of a polynomial function cross, intersect, or just touch the x-axis. All right. So that's what we are going to talk here. Now, previously, when we were working with quadratic equations and quadratic functions, we had found the zeros of a quadratic function by solving for x. By making the y value equal to 0, we either use the factoring method, or if it was not factorable, we use the quadratic formula to solve for x, and we came up with the x values, right? The x-intercept, so to speak. Now, for higher order polynomials, it may not be easy to factor the polynomials easily. In that case, we will have to just learn different techniques or ways of first uh, identifying possible zeros, possible roots of the function, and then using the synthetic division, we will learn how to select the specific zeros of the polynomial function. So in this chapter, we are first going to learn a new theorem called the rational zero theorem to find possible rational zeros. Then we will find the actual zeros of a polynomial function. Then we learn to solve polynomial functions. We'll talk about using the linear factorization theorem. So another theorem is coming up after the rational zero theorem to find polynomials with given zeros, and then a rule of signs. It's called the Descartes rule of signs. So we will discuss that. So this chapter is going to be pretty long and a lot of theorems to learn. All right. So we'll start with the rational zero theorem. The rational zero theorem tells us a way of finding possible rational zeros. So it'll give us a bunch of values which could be the zeros of the function, or they couldn't, but it kind of shortlists, it narrows us down to a list from which there would be some which would be zeros of the polynomial function and some which won't. So we learn about the rational zero theorem and what it's about and how it helps to come up with the possible rational zeros. We will now start with the rational zero theorem. Now, what the rational zero theorem does is it helps us narrow down the list of possible zeros that a polynomial function can have. That is, the number of x-intercepts, that the number of possible x-intercepts that the graph of a polynomial function will have. Now keep in mind that the x-axis stretches from negative infinity to positive infinity. It could have an infinite number of x values. This theorem, the rational zero theorem, helps us come up with just a handful of possible x-intercepts or the zeros of a polynomial function. All right. So we are going to learn the technique of deriving that shortlisted set of x-intercepts. How do we do that? We will look at the last coefficient of an ordered polynomial and the first coefficient of an ordered polynomial, and then we will create some ratios using those two coefficients, and we will come up with a short list of possible zeros. Not all of them will be zeros. We have to work further to pick the exact zeros of the function, but uh, it'll give us a manageable size of possible zeros. Now what I've done here is I have an example written out, and we are going to walk through this example to obtain that possible rational zeros list. All right. Now what this theorem says is, in order to find your rational zeros, look at the last coefficient of your ordered polynomial and look at the first coefficient, that is the leading coefficient of your polynomial. And once we have that, we will need to factor them out and then create ratios out of those factors, and that will be our narrowed down list of possible rational zeros. So I have this example here. Let's walk through it. Now, let me pull up my pen. All right. The last coefficient we must always denote with the letter P. All right. And the first coefficient we are going to denote with the letter Q. All right. Because as you see over here, they have used the ratio P over Q. What is P and what is Q? P is the last coefficient and Q is the first coefficient of our polynomial. So in this example here, in this example here, P is going to be the last coefficient, which is a 4, and Q, the first coefficient in this case, is -1, correct? It's negative x to the 4th, that means the coefficient is -1. Now once we have the values for P and Q, we have to take each of these values and factor them out. We have to write it in all the different factors of those values. So the factors of 4 are plus and minus 1, plus minus 2, and plus minus 4. All right. You have to use both the signs. All right. Both the signs of the factors. So it's not just plus 1, just 1, 2, and 4, but plus minus 1, plus minus 2, plus minus 4. So here I have written them out separately. Plus 1, minus 1, plus 2, minus 2, and so on. For Q, you have to do the same thing. -1 was the value of Q, and the only factors of -1 would be plus 1 and minus 1. All right, so I've written it out separately, plus 1 and minus 1. Now, once we have done that, the next step is to form ratios using P and Q, and it's always P divided by Q. All right. So how do we go about it? Take all your P values and divide them first with the first factor of Q, which is plus 1. So 1 over 1, -1 over positive 1, plus 2 over plus 1, -2 over plus 1, 4 over plus 1, -4 over plus 1. Once we've completed that, all right, up to this point, we start again with the next factor of Q, in this case -1. So 1 over -1, -1 over -1, 2 over -1. So, and if there were more other factors of Q, you would keep doing this, go through that process of coming up with the ratios. And we see that some of the values are repeated. right? We see some of the values are repeated. So there's 1 divided by 1 is 1. And then we have here -1 over -1 is also 1. All right, so it's the same number, 1 from here and 1 from here. So once we have come up with all the ratios, all right, pick each unique ratio and write it. So it's going to be plus minus 1, plus minus 2, and plus minus 4. So that means we have come down from an infinite set of numbers, from an infinite list of x values on the x-axis. We have narrowed it down to just 6 values: plus minus 1, plus minus 2, and plus minus 4. Now these are the possible zeros. Not all of them are going to be the zeros necessarily. All right, it'll only be some of them will be zeros, and we will go through more steps, more process. We will use the synthetic division, as you will see in the next few slides, to come up with the actual zeros of the polynomial function. Let's go through this example now of finding zeros of polynomial functions. Now we are going to start using the possible rational zeros theorem, that is the P over Q method, to determine all possible rational zeros that we can get from this function. So function is x cubed, right? It's x cubed plus x squared minus 5x minus 2. So the way we go about applying the rational zeros theorem is we do the P over Q. And I'm just trying to pull up my pen here. So it's P over Q, right? P over Q. But what is P and what is Q? P is the last term, or rather the coefficient of the last term in our function. This is P, right? This is P. What is Q? Q is the coefficient of the first term of our function. In this case, the first term has a coefficient plus 1, right? It's positive 1, and that is our Q. So let me just write that here. Q is equal to plus 1. And now in the next step, we are going to find the factors of P and Q and then create some rational values, which by taking the P values and dividing them by Q. So we have Q equals plus 1. So write it here. We have P and Q. P is equal to -2. So all the factors of -2 would be plus minus 1 and plus minus 2. So these are the 4 factors of that we can get of -2. Plus 1, minus 1, plus 1, minus 1, plus 2, and minus 2. For Q, whose value is positive 1, we will get plus minus 1. Plus minus 1, 2 factors, all right, plus minus 1. So we take all our P values, every P value, and it's better to write it out instead of combining plus minus to the numbers. It's better, I think it helps if we write it down. So just a second, I'm going to write here the values of P separately. So it's actually plus 1, plus 1, minus 1, plus 2, and minus 2. And likewise for Q, it's plus 1 and minus 1. So when we get all the combinations of P and Q, right, it'll be easier for us to get it. So it'll be plus 1, all right, 1 over 1, negative 1 over 1, 2 over 1, and negative 2 over 1. All right, that's one set. And then we have again 1 over negative 1, negative 1 over negative 1, 2 over negative 1, and negative 2 over negative 1. All right, and then we will come up with the factors when we uh, simplify the signs and everything. We will have four values: plus 1, minus 1, plus 2, and minus 2. And those are going to be the list of possible rational zeros. Now, not all of these are going to be rational zeros. All right, only maybe a few of them, but this is a short-listed set, all right, from which we can determine which ones are actually the zeros of this function. So let's see how they've worked out the solution, whether they've followed the same method and whether they got the same possible rational zeros. It says we begin by listing all possible rational zeros, and they use the same method here. They first factored P, and they haven't shown their work here. Well, we have shown our work here. So we took the value of P, negative 2, and we factored them, and we got four factors here. And then for Q, which was had a value of positive 1, we came up with two factors, plus 1 and minus 1. We wrote them down here, and then we created these, put together them together in ratios, and we came up with four values. And as we see here, they too came up with four values here. Here they've put it together in ratio form. So now, to determine out of these four values which ones are going to be rational zeros, actual zeros, we will be using the synthetic division method to see if we can find a rational zero among the four possible rational zeros that we have so far shortlisted. Now, remember what the theorem says that we learned before, that when we perform the synthetic division, and if we get a remainder of 0 after performing the synthetic division, then that C, which we use to perform the synthetic division, will be a zero of the function. All right. So for the next slide, we are going to take these four values and perform several synthetic division operations to determine if we are getting a remainder of 0. Whichever one of these will give us a remainder of 0, that will be a 0 of this function. All right, so let's see what happens in the next set of slides. So in this slide, we bring our possible rational zeros that we obtained by using the rational zero theorem, and we will now go on and perform the synthetic division on our polynomial, the coefficients of our polynomial, and determine which one of these are the actual rational zeros. So first, we see they have used the negative values. They started with negative 2, looks like, and then negative 1. So they've just decided to go from the smallest to the largest, probably. So over here, if you remember the method of performing synthetic division, we just work with coefficients. These were the coefficients of the different terms of the polynomial given to us. So it was 1, all right, I think it was x cubed plus x squared minus 5x minus 2. It was something like that as based on the signs shown here. So these were the coefficients, and these are the c values. All right, remember c, x minus c, which where when we perform the synthetic division, the c values goes on the left hand side of the separator, or the synthetic division operator here. So we put -2, and then we perform our synthetic division. We first bring the +1 down and write it below the line. All right, so 1 is written as is, and then it's -2 times 1 is -2. We write that value above the line, right below the second coefficient, all right, the second term here, and then we add 1 minus +1 plus -2 is -1. So we get a value of -1 below the line, and then again we take this c value, which is -2, and multiply it by -1, we will get a +2. -2 times -1 is +2, and that's why we have a 2 below the -5. All right, performing the addition, -5 plus 2 gives us a -3. We again multiply -3 by -2 to get a +6. We write that +6 below the last coefficient in our list. So -2 plus 6 is +4. Now always remember the last value below the line, that last value is always the remainder, and we see the remainder is not 0. So that means -2 is not a 0, even though it was in the possible list of rational zeros. But after performing the synthetic division, we realize that since the remainder is not 0, therefore -2 is going to be crossed out. It's not, okay, -2 is not a 0, not an actual 0. Why? Because the remainder, all right, the remainder is not equal to 0. All right, is not equal to 0. Actually, let me just change this here. This is also not equal to sign, but it's the not equal to sign in computer programming. So I'll change it to not equal to here. All right, so now we take the -1, the c value of -1, all right, and do the synthetic division on the same set of coefficients. So when we do that, we see that the remainder this time is a 3. It's still not 0, so that tells us -1 is also not a 0 of the function. All right, sorry. This is the one I should be crossing out. So neither -2 nor -1 are zeros. So now we have, so let's cross this out here. This one is not, this one is not. So now we are left with 1 and 2. So in the next slide, we will perform the same synthetic division using 1 and 2 and see which ones, if at all, produce a remainder of 0. That will be, or those two. If both produce a remainder of 0, then both are going to be possible zeros. If one, then only one. So let's see what happens in the next slide. Here we are performing our division, the synthetic division, by the remaining two possible zeros. So 1 and 2, right? We have found that -2 and -1 are not rational zeros because they didn't produce remainder of 0 when we performed the synthetic division. So we had 1 and 2 remaining. So we do the synthetic division by 1 and we see that the remainder is a -5. Therefore, this 1 is neither a 0 of the function. All right. So I'm going to cross that out. And now, all right, so this wasn't 1, all right, wasn't either. So now we just left with 2. So I'm going to walk through the synthetic division this time. All right, so we wrote the 1 below the line. All right, 2 times 1 is 2. So we wrote the 2 below the plus 1 and we added them. 1 plus 2 is 3. 2 times 3 is 6. Positive 6. We wrote the 6 below the -5. -5 plus 6 is plus 1. 2 times 1 is 2. So we get positive 2 and -2 plus 2 is 0. So now we found a 0 of the rational of the polynomial that we were working with. All right, so we have found a rational 0 at x equals 2. So what does 0 again mean? It means that the graph will touch or cross the x-axis at x equals 2. All right, that's what 0 means. All right. Now that we have found a 0 of the polynomial x cubed plus x squared minus 5x minus 2, we have to go through the exercise of rewriting this in factor form using the information we obtained from the synthetic division. All right. Now, because the remainder is a 0 in this case, it tells us that one of the factors of the of this polynomial is going to be composed using this 2 with which we divided the polynomial. All right. How do we go about that? All right. How do we compose a factor using this 2? Remember, 2 is c, right? And also recall that we got the c from this form x minus c, which was going to be the divisor of the polynomial. All right. The divisor is in the form x minus c. All right. And then we just pick the value of c from this x minus c divisor and used it to perform the synthetic division. We wrote the 2, all right, and we performed the synthetic division. So here, since we divided by 2 and we got a remainder of 0, all we need to do is put back this 2 into the x minus c form, and that will be one of the factors of the polynomial. So all I'm going to do is I'm going to write my x, and then there's a minus sign in the x minus c form, and then write the value of c, which is a 2, and that becomes one of the factors of the polynomial. All right. The other factor is composed from the quotient of the synthetic division. All right. So here we see 1 plus 3 plus 1. These represent the coefficients of the quotient. The last value in the synthetic division gives us the last value on the right hand side, extreme right, is the remainder, and all the other numbers to its left represent the coefficients of the quotient, right? But these are just the coefficients. We have to give these a variable with the appropriate exponent and then put it in as, or write it as one of the factors of the polynomial. But we know the variable that we are going to give it is x, but what exponent are we going to give here? All right. The way to go about it is to look at the exponents of the initial function, of the original function. The original function had x cubed for the first term, then x squared, then x to the 1, and then x to the 0 was the variable and exponent of the last term. And because anything raised to the power 0 is a 1, that's the reason we don't see a variable in the last term of a polynomial. All right. So in order to come up with the exponents of the quotient, look at the exponent of the original function and write the exponent, make the exponent 1 less than the original function. All right. So in the first term in the original polynomial was a 3. So the first term in the quotient is going to be 1 less than 3, which is a 2. For the second term of the quotient, it's going to be 3 times x to the 1 because the original function had 2 as an exponent in the second term, and the last term is just going to be plus 1. All right, so x squared plus 3x plus 1, just surround it with brackets and write it as one of the other factor rather of this polynomial. Okay, so now we have these two factors for x cubed plus x squared minus 5x minus 2. Now we can make x minus 2 equal to 0, and we have x equals 2 as one of the intercepts of the graph. However, we have to solve for x squared plus 3x plus 1 and come up with the other values of x. So that's going to be the next step. All right. So we have x squared plus 3x plus 1. We have to solve for x for this factor. Now, if first, see if you can use the factoring method to solve for x. If you cannot, then we'll have to just use the quadratic equation that we learned before. All right, so let me just write the quadratic equation here. Minus b plus minus square root over b squared minus 4ac over 2a. That's our quadratic equation, which we are going to use. Rather, the quadratic equation formula, which we are going to use in the next slide to solve for x in x squared plus 3x plus 1. So we've solved for x using the quadratic formula here, which is minus b plus minus square root over b squared minus 4ac over 2a. We have to determine the values of b, a, b, and c from this polynomial or this quadratic polynomial here. What is a? A is the coefficient of the first term, which is a 1. B is the coefficient of the second term, which is a positive 3. And C is the last term, which is 1. So now that we have those values, we plug those values into the formula here. All right, so have the formula written out. All right, that way you can it'll be easier for you to plug in the values correctly. So minus is in the formula, so we have to put the minus, and then b has a value of 3, so write the 3, plus minus, then the square root sign, b squared, so 3 squared, minus 4, it's minus 4, a has value 1, and c has value 1. That's why 4 times 1 times 1 divided by 2 times a has value 1, so 2 times 1. All right, so we have minus 3, then plus minus 3 squared is 9, minus 4 times 1 is 4. 9 minus 4 is 5. So we have 5 under the radical sign. All right. Divided by 2 times 1, 2. So the zeros of f of x equals x cubed plus x squared minus 5x minus 2 are the 2, which we found through synthetic division, and then minus 3 plus square root over 5 by 2, and minus 3 minus square root over 5 by 2. So there are 3 zeros, 3 real zeros of this polynomial function. Where is it? This polynomial function. This was the original polynomial function. So the graph will touch the x-axis not only at 2, but also whatever these values evaluate to. Minus 3 plus square root over 5 divided by 2, and minus 3 minus square root over 5 divided by 2. You will need your calculators to get the exact numbers that these evaluate to. We will now go through a couple of properties of the roots of a polynomial equation. Now, the first property states, if a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. Now, all this means in simple terms is the number of solutions that an equation, a polynomial equation, is going to have will be equal to the degree of that equation. What does degree mean? Degree is the highest exponent of the polynomial. That represents the degree of the polynomial, correct? So the number of solutions you can expect an equation to have will always be equal to whatever the highest exponent is in that polynomial. We've already seen that in quadratic polynomials, where the highest power is 2, when we solved quadratic equations, we always came up with 2 solutions. Likewise, if the highest power is a 3, it'll have 3 solutions. If the highest power is 9, x to the 9, then it'll have 9 solutions. If it's x to the 100, it'll have 100 solutions. That's all that this property, the first property, is stating. Now, we have a phrase here. It says counting multiple roots separately. What does that mean? We have seen instances, we have solved some equations which looked like this: x plus 2 squared equal to 0. The way we go about solving this is we write x plus 2 whole squared as 2 separate factors, x plus 2 times x plus 2 equal to 0. Then we make each factor equal to 0 and solve for x for each factor, right? So we make each factor equal to 0. The first factor gives x equals negative 2, and the second factor gives the same value, x equals negative 2. So even though the solutions are the same, we need to count them separately because they come from 2 separate factors. All right. Therefore, even though, again to repeat, even though it is the same value, the solution has the same value, we should still count them separately in order to make this property valid. And that's what it means when we say counting multiple roots separately. All right. Property number 2 says if a plus b times I is a root of a polynomial equation with real coefficients b not equal to 0, then the imaginary number a minus b times I is also a root. Imaginary roots, if they exist, occur in conjugate pairs. Now, what this is saying is if one of the solutions of a polynomial equation happens to be an imaginary number, for example, I is an imaginary number. So if one of the solutions is an I, then by default, automatically its conjugate, which is negative I, a negative I, is also going to be one of the roots, one of the solutions of that polynomial equation. Likewise, if one of the solutions is negative 2i, its conjugate is positive 2i, will by default be the solution of the same polynomial equation. All right, they always occur in pairs. That's why they are called conjugates of each other. They always occur hand in hand. Minus 2i plus 2i. Likewise, if we have something like 3 minus, I don't know, 3 minus I, then its conjugate is 3 plus I, will also be a solution of the equation. Now, what or how does an imaginary root affect the graph of a polynomial? All right. We know that the solutions of that we find of x, all right, when we make the polynomial equal to 0 and solve for x, that means those are the x-intercepts of the graph. That means those at those x points, x values, at those points of x, the graph will touch or cross the x-axis. But when the x value is an imaginary value, what it means is the graph will never touch the x-axis. That means these x-intercepts are only in theory, only in imagination. They will never touch the x-axis. So if it was a quadratic equation, all right, for a quadratic equation, if we come up with imaginary solutions, the graph is the parabola is going to look something like this. You see, if a parabola is positioned here, it'll never touch the x-axis. Its vertex is way above the lowest point of the graph of the parabola, is way above the x-axis, and then it turns up. It's never going to touch the x-axis. Likewise, we can have a graph, downturn graph also, not touching the x-axis ever. That means these the equations of these graphs have x values. That means the solutions of x are imaginary. All right. Here's an example of an even higher order polynomial to work on using all the theorems and methods that we have learned to come up with zeros and the roots and so on. So what is the function given to us? It's x to the power 4. So this is of degree 4. This polynomial is of degree 4. X to the power 4 minus 6x cubed plus 22x squared minus 30x plus 13 equal to 0. Again, we start with the possible rational zeros to narrow down on the zeros of a polynomial, possible zeros of a polynomial. And we use the P over Q process. So what is our P here? Again, P is going to be the last term, the coefficient of the last term of the polynomial, an ordered polynomial, and Q is going to be the coefficient of the first term of our polynomial. So in this case, q equals 1 and p equals 13, positive 13, all right, and positive 1. So now we have to create factor p and q. So the factors of p would be plus minus plus 13 and minus 13, or minus 13 and plus 13, however way you want to write that. And q is going to be plus 1 and minus 1. So now we have to create all possible combinations of p over q using these values. So 13 over 1 and negative 13 over 1 is going to be the first set, and then 13 over negative 1 and negative 13 over negative 1 is going to be the next set. And then here we have the p over q's represented. So we have 4 possible rational roots: 1, negative 1, 13, and negative 13. We will use synthetic division to test the possible rational zeros. So now that we have narrowed down the possible zeros, we will use these as the C values in a synthetic division. All right, so that's what we are going to do in the next slide. So we have the 4 shortlisted values that we got from using the rational zeros theorem, which were 1, negative 1, 13, and negative 13. So we are going to use them as the C values and perform the synthetic division on the original polynomial function. So the original polynomial function was like this, right? So I'm going to write here just this was x to the 4th, this was x cubed, this was x squared. Then we had an x, and the last one is x to the 1, and the last one is x to the 0, right? So when we perform the division, all right, what do we see here? 1, the first term, the coefficient, is written below the line 1. Then negative 1 times 1 is negative 1. Write it below the next number here. Negative 6, negative 1 is negative 7. Negative 7 times negative 1 is a positive 7. Do the addition here. 22 plus 7, positive 29. And we continue with the process, and we see here that the remainder is 72. It's not a 0. So negative 1 is eliminated, correct? So I'm going to cross that out. Negative 1 is eliminated. Now we work with the next value, which is positive 1. All right. So they're working with positive 1 here. Same process. Now positive 1 shows a value of 0 for the remainder. All right. So we have obtained a 0, which is positive 1. All right. So this is our remainder. All right. And if the remainder is 0, that means 1 is a possible, is not possible. It is an actual root. So what we do is we create one of the factors of the polynomial using 1 in the x minus c form. So one of the factors is going to be x minus this one here, because the form is x minus c. All right, so we got x minus 1 as one of the factors, and the other factor is going to be from this quotient. All right, so we can compose the quotient using the values we got here below the line. All right, so this is going to be 1 less, remember the first one was x to the 4th in our original polynomial. So the quotient is going to begin from x cubed. So we will have x cubed minus 5x squared plus 17x minus 13. All right, and that's exactly what they got here. All right, so we can rewrite the equation in factored form as x minus 1, and the rest, the other factor, is obtained from the quotient that we got from the synthetic division, which gave a 0 for the remainder. So x minus 1 is a factor in the simplest term, is the simplest factor. We don't need to worry about it anymore. We just focus on this other factor, which is in a polynomial of a higher order, x cubed minus 5x squared plus 17x minus 13. So we have to factor this polynomial further, and we start the process all over again by first applying the possible rational zeros theorem. All right, so we now solve x cubed minus 5x squared plus 17x minus 13 equal to 0. See, they repeat the process here. We list all possible rational roots. Now this time we have our p equals negative 13 and q equals positive 1. All right, we have to take all factors of negative 13. So it's going to be negative 13 and positive 13, the factors of negative 13. And then q is going to be plus 1 and minus 1. Now I left out the plus 1 minus 1 for p, which is not correct. So I'm going to rewrite this, the factors for p, my mistake. All right, 1 plus minus 1 should always be the one of the factors. All right, so don't miss that. I should have written it plus 1 plus 1 minus 1 plus 13 minus 13, right? These are the four factors of p, and q, this is only one, so plus minus 1. So now they have formed ratios by doing p over q, and we get possible rational roots are 1, minus 1, 13, and negative 13. So now that we have shortlisted the possible rational zeros or rational roots, we are going to perform the synthetic division on this particular polynomial. All right, x cubed, not the original one, on this polynomial that we got from the quotient of the previous synthetic division. So now we'll be performing the synthetic division. Remember what our possible zeros were. It was plus minus 1 plus 1 minus 13 plus 13, correct? Now, when we first started the synthetic division on the original polynomial, we saw that negative 1 did not give a remainder of 0 on the original polynomial. All right, we had discarded that, we had eliminated negative 1. Now, since it did not work for the original polynomial, we can eliminate it completely from our list. So although negative 1 did show up as a possible 0, or as a possible root, a possible 0 of the x cube polynomial, we can eliminate it because it didn't work for the original one, the original polynomial of degree 4. So I'm going to just eliminate this from our list. So now we have even a shorter list of plus 1, minus 13, and plus 13. So what they do here is they use plus 1 and perform the synthetic division. So over here we have x cubed, right? This 1 corresponded to x cubed. We had x squared corresponding to the place for negative 5, then x to the 1 and x to the 0, right? And once we perform the synthetic division, all right, so the synthetic division, we see that the remainder is going to be a 0. So that means positive 1 is again one of the roots of this polynomial. And that tells us that 1 is of multiplicity 2, at least over here. All right. It's of multiplicity of at least 2. We get 1 as another possible, not possible, another actual 0. And this is our quotient here. So when we write this and represent this in factored form, we will have x minus 1. See, this is the original polynomial that they put here, x to the 4th. And so we have x minus 1 obtained from the previous synthetic division, and then x minus 1 from this synthetic division, and this factor here, x squared minus 4x plus 13, is obtained from the quotient values of the synthetic division. So x squared minus 4x plus 13. So now we are left with finding or solving x for this quadratic polynomial, quadratic factor, so to speak, x squared minus 4x plus 13. Now we are focused on this quadratic expression here, x squared minus 4x plus 13. Now when you have a quadratic polynomial, then first see if you can factor it using the factoring method. All right. So 13, there's no way we can find factors of 13 which will add up to negative 4. So that means this is not factorable. We have to proceed with using the quadratic formula, which is minus b plus minus square root over b squared minus 4ac, this whole thing divided by 2a. And what are our a, b's, and c's? We again just focused on this factor, this quadratic factor here. So our a is 1, b is negative 4, right? B, this is our b, right? This is b, and c is positive 13. It's 13. So they plug in the values here. All right, negative, and so it's negative of negative 4. Let's not skip this step here. How did they get positive 4 here? They plugged in negative of negative 4. B is negative 4. So negative of negative 4 is a positive 4, and they wrote the 4 here. That's why we see a positive 4. And then plus minus, and then square root over negative 4 squared. Again, please use your brackets around the b. All right, the variable that you're plugging in, negative 4 squared minus 4 times a is 1. A is 1. And c is positive 13. So we have a 13 here divided by 2 times a being 1. We have 2 times 1. So 4 plus minus, this is 16, positive 16 minus 13 times 4 is 52. All right. So 16 minus 52 is square root over negative 36. All right. So what happens here? We have a negative inside a square root, underneath a square root. Therefore, this is going to give us an imaginary number. All right. An imaginary solution for x. All right. So we end up with, when we simplify, 4 plus minus 6i, right? 36. Negative 36 is simplified as 6i. So 4 plus minus 6i divided by 2 equals 2 plus minus 3i. All right, so we get a solution set which is 1, 1, and then 2 plus 3i, and automatically 2 minus 3i, the conjugate. Again, any quadratic equation will produce two solutions. All right. So in this case, one is a positive, the other one is the negative, the conjugates, because this is in the form a plus b times I. So these are the solution sets of the original equation. All right. So of this, 1 and 1 are the are real roots. These are imaginary roots. Now we'll talk about yet another theorem called the linear factorization theorem. Now all that this theorem is about is that if we have a polynomial function where n is greater or equal to 1, that means n being the exponent of the leading term in the polynomial function. In other words, n represents the degree of the polynomial, and that has to be greater or equal to 1. Then we can factor the polynomial and rewrite it as a sub n, where a sub n is a constant value. It's going to be a numerical constant value times x minus c1 times x minus c2 times x minus c3 times x minus c4, all the way up to x minus c sub n, and n being again the exponent of the leading term. So if you recall, we discussed previously that a polynomial of degree n will have n number of roots. Now, those roots, which are represented by c, could be the same, exactly the same value, or it could be imaginary values. They need not be distinct. So what it says here is it can be written in this form where c sub 1, c sub 2, c sub n are complex numbers, possibly real and not necessarily distinct. So we could have uh, factors x minus 2 getting repeated in this factored form. So we could have x minus 2 times x minus 2 times maybe another x minus 2 and then some other factor x plus 3. And most of them will be real but could also be imaginary. So in words, or in simple terms, what it says is an nth degree polynomial can be expressed as the product of a non-zero constant, which is going to be a sub n, and n linear factors, where each linear factor has a leading coefficient of 1. Linear factor means each factor has to be x minus something. It cannot be x squared or x cubed, all right? It has to be represented as a linear expression, x minus c. Otherwise, it's not fully factored. Let's look at this example here. It says finding a polynomial function with given 0. So if they give us some roots of a polynomial, all right, given zeros meaning roots or the c values of the polynomial, as well as an evaluated value at a certain x values, then how do we come up with a polynomial uh, in the proper polynomial form? All right. So let's read the question. It says find a third degree polynomial function. That means third degree would mean n equals 3. So it would start with x cubed. So find a third degree polynomial function f of x with real coefficients that has minus 3 and I as zeros, and such that f of 1 equals 8. All right. So basically it has given us the some roots, all right, -3 and I. And it has also given us an evaluated value of 8 at x equals 1. So when x equals 1 in that function, whatever the function may be, we have to come up with that. If we input 1 into the function and evaluate it, then we will get 8 as a y value. All right. So how do we go about that? How do we derive it from just this information? So remember, this says it's a third degree polynomial, which means that if n equals, okay, if I'm just trying to pull up my pen here, give me a second. Okay, so n equals 3. How do I know that? From this piece of information here. It's a third degree polynomial. So when n equals 3, in factored form, it's going to have x minus c sub 1 times x minus c sub 2 and x minus c sub 3, and over here it's going to have a sub n, right? That's the constant, the leading constant. All right, and then everything else will be in factored form, and we stop here, right? Because n equals 3, we will have 3 roots. And what are the roots given to us? One is -3. So let's say c sub 1 equals -3, and then it says it has I. All right, it has I. So c sub 2 equals I. So we got 2 of our c values. What we need another c value, right? Okay, because we have c sub 1, c sub 2, and c sub 3. What about the other c value, the third one? Now, if you recall, if we have an imaginary root, all right, if we have an imaginary value for the root, then its conjugate is also one of the root. They always appear in pairs. Imaginary numbers as roots will always appear as in pairs. All right. So if we have I, then its conjugate is negative I. All right, its conjugate is negative I. So now we applied that fact, that theorem, basically, that if we have an imaginary root, then its conjugate will also be one of the roots of the polynomial. So we have got -3, we got I, and negative I, which is a conjugate of I. All right. So once we do that, we can just plug them into. So a sub n we don't know yet, so I'll just write it as, keep it as a sub n, and then x minus, remember it's c1, which is -3, and minus is part of the form of the factor, so I have to write it as -3. All right, -3, that's one of the factors. Then x minus, the second one, c sub 2, is I. So I'll write minus I. And then the third one is x minus I. X minus I. That's c sub 3. All right. So we have at least plugged in the different values of c and come up with 3 factors of this polynomial. So now let's go down and see how they work this. It says because I is a 0 and the polynomial has real coefficients, the conjugate minus I must also be a 0, right? And that's what we've done here. We said c sub 2 equals I, and therefore because I is imaginary, its conjugate is also going to be one of the roots or one of the zeros of the polynomial. So we got minus I. We can now use the linear factorization theorem, and they've written it as a sub n times x minus 3 is x plus 3. then x minus I, and then x minus minus I is x plus I. So now when you multiply this out, all right, so we can FOIL this, all right, part by part. So let's do the let me do that on the side. It'll be easier for you to understand how they came up with x cubed plus 3x squared plus x plus 3. Let me do that here. So I'm going to first, here we go. I'm trying to pull up a different color on the pen. Bear with me, please. Okay, so I'm going to start with x minus I and x plus I. It's going to make it easier. All right, so x minus I times x plus I. Now, x minus I times x plus I will give you the difference of squares, right? So we have i's in both the factors, and one is a minus and one is a plus. So it can take the form a squared minus b squared. That's the difference of squares. So I'm going to use that um, factoring method, that factoring and expansion theorem or fact that we know already, and write it as x squared. Then the middle sign is going to be minus difference of squares, x squared, and then I squared. Okay, I squared. So we know x squared stays as x squared, then minus I squared is a real number, right? I squared means what? What does I squared? I is square root over negative 1. Negative 1. When you square that, square root over negative 1 squared is going to be negative 1. So even though I is an imaginary number, I squared is a real number. Negative 1 is a real number. So I'm going to write it as minus minus 1. All right. So we will have x squared plus 1. All right. So x minus I, all right, x minus I times x plus I amounts to x squared plus 1. So I'm going to replace this by kind of losing my pen here. So x squared plus 1. So now we can do the foiling with x plus 3. So I'm going to erase, make some space here. Maybe work it out here. So we have x plus 3 times x squared plus 1. I'm going to write out the FOIL, all right? So x times x squared plus 1 plus 3 times x squared plus 1. So we'll have x cubed plus x times 1 is x plus 3x squared plus 3. All right, and that's what they got here after they put the terms in proper order. They got x cubed plus 3x squared plus x plus 3, and then the a sub n stays here. So we have expanded the factors. We have multiplied out and expanded the factors and written it in polynomial, converted the factors into a polynomial. We need to find a value for a sub n. Now, in order to do that, we are going to use this piece of information given to us, f of 1 equals 8. So in the next slide, we'll see how to do that. All right. So now in the previous slide, when they stated the question to us, they gave us a piece of information saying that f of 1 equals 8. That means when x is going to take a value of 1, the y value is going to be 8 in the polynomial that we are going to find. So we already found the expanded form of the factors of the polynomial, and we need to find this leading constant a sub n. In order to do that, we are going to use this part of the information, this piece of information that was given to us. All we need to do is we write it out in this form, and then we replace all the x terms, the x values, or rather the x variables in this polynomial by 1, and make f of x the other side equal to 8. So that's what they've done here. F of 1 is equal to a sub n, and they have replaced all the x values by 1. So we have a sub n times 1 cubed times 3 times 1 squared plus 1 plus 3 equals 8. So we have a sub n. If we add these, if we simplify what is within the brackets now, we have 1 cube is 1, 3 times 1 squared is 3, this 1 stays and this 3. So 1 plus 3 plus 1 plus 3 is 8 times a sub n. All right, 8 times a sub n equals 8. So we have solved for a sub n. We have found the value of the leading constant, which is 1. And once we get that, we are pretty much complete. We just need to plug in that value into the polynomial in place of a sub n. And because it's 1, we can just write it as f of x equals x cubed plus 3x squared plus x plus 3. Now, if you wrote it as like this, f of x equals 1 times x cubed plus 3x squared plus x plus 3, and then multiplied it out and wrote it like this, that's fine too. All right, in fact, that's better. That way I know how you have obtained f of x equals x cubed plus the final answer, the final polynomial. Now, one last rule to study before we end this video podcast. It's called the Descartes rule of signs. Now, this tells us how many positive and how many negative roots we can expect from a polynomial. Previously, we learned how to narrow down the possible rational zeros of a polynomial function, right? Here, this rule will help us determine how many positive and how many negative roots we can expect from a polynomial. So I'm going to read through this, and then once we discuss an example, it'll become more meaningful. But let's just go through the statement here. It says, let f of x be this polynomial a sub n times x sub n all the way to a sub 0, be a polynomial with real coefficients. Then the number of positive real zeros of f is either the same as the number of sign changes of f of x, or less than the number of sign changes of f of x by a positive even integer. If f of x has only one variation in sign, then f has exactly one positive real zero. So just to summarize, what they're really saying is the number of positive real zeros. In order to determine the number of positive real zeros, we have to look at the sign changes between the terms. All right, if this starts with a plus, all right, and then if this were a minus, then that would be regarded as a sign change. Then if the next one had a minus, that's no sign change. There's no sign change. Minus to minus, no sign change. If the next one were a plus, then that would represent a sign change. All right, negative to positive. So in other words, what we are doing here is we are looking at each term, looking at the sign of each term and determining whether it's a change from the previous term. All right. Now, as far as negative real zeros are concerned, the Descartes rule of sign says the number of negative real zeros of f is either the same as the number of sign changes in f of negative x or less than the number of sign changes in f of negative x by a positive even integer. If f of negative x has only one variation in sign, then f has exactly one negative real zero. So to determine the negative real zeros, we have to plug in negative x in the function and look at how the signs are from term to term, and based on that, on the sign changes, we can determine the number of negative real zeros. All right, so we'll go through an example and you will see how we can determine the positive and negative real zeros. So let's look at this example here. It says determine the possible number of positive and negative real zeros of f of x in this polynomial. All right. So first we'll start by looking at the positive real zeros. So to determine positive real zeros, we just need to look at the polynomial exactly as given and see how many sign changes are involved. All right, so let me go through that process here. We have to look at it term by term. So the first one is positive, right? So there's a positive and then the next one is negative. So that's a sign change. Then negative to positive from the second to the third term, that's a sign change. So two sign changes. Then positive to negative, that's three sign changes. And then negative to positive, four sign changes, right? Four sign changes. So let's look at the solution. It says to find possibilities for positive real zeros, count the number of sign changes in the equation for f of x. And that's exactly what we did here. We noted the sign changes from term to term and we found there were four sign changes. All right, four sign changes. So it says there are four variations in sign. Now, because there are four variations in sign doesn't mean that there are going to be four positive real roots. It could be less. By how much? By an even number. It would be 4 or a number. Um, it could be either 4, the number of variations in sign, or it could be an even decrease from 4. So in other words, what that means is, again, I'm trying to pull up my pen here. Okay, 4 or 4 minus 2 or 4 minus 4. All right, so you decrease the number of variations by an even value. Even value, that's important. All right, not an odd value, an even value. So the number of positive real zeros could be the total number of variations, which is 4, or it could be 4 minus 2, which is 2. All right, 4 minus 2 is 2, or 4 minus 4 is 0. So this polynomial could have 4 positive real zeros or 2 positive real zeros or 0 possible real zeros, right? Now, as far as negative real zeros are concerned, we cannot work with the original polynomial function as was given to us. we have to change it a little bit in the sense that we have to replace the x in f of x with negative x and rework this polynomial. And that's exactly what they did as the first step in determining negative real zeros. They took the polynomial of f of x, they replaced it by negative x and reworked, all right, the polynomial. So we have negative x, they replace this x with negative x to the power 4 minus 14 times negative x cubed plus 71 times negative x squared minus 154 times negative x plus 120. And when we do that, we negative x to the power 4 raised to an even power is going to be positive x to the fourth. This is going to be minus 14 times minus x cubed. So plus 14x cubed minus minus becomes a plus, and then, so let me just write this here. This expression minus x cubed is negative x cubed. All right, it's negative x cubed, negative x cubed. All right, so negative 14 times negative x cubed is positive x cubed. And then we have plus 71 times negative x squared. This is even power, so this will become positive x squared. So 71 times x squared is x squared, and then minus 154 times minus x is positive 154x, and then the last one is plus 120. And now we can observe the change in sign. So doesn't look like there's any change in signs. Let's go through all the terms one by one. So we have positive here. So from the first term to the second term, no change. Second term to the third term, no change. Third to fourth, no change. Fourth to fifth, no change. So there are 0 variations. When we replaced the x in the function with negative x and reworked the polynomial, then we found there are no variations in sign. Therefore, there are no negative real roots for f. So the number of positive roots could be either 4 or 2 or 0 that we saw in the previous slide. And as far as negative roots are concerned, negative real zeros are concerned, it's going to be 0 negative real roots because there were 0 variations when we replaced the x with a negative x.